Well, hey everyone, welcome to lesson 2, and in this lesson we're going to take a deeper look at primitives, Java primitives specifically. We're going to learn a ton in this lesson, and I want to kind of give you a forewarning for this lesson as well as a lot of these very early lessons. A lot of times people come in and they're ready to build an app or something, right? They want to release something to the Google Play Store, the Apple Store, whatever. And we're just not quite ready to do that, right? We have to learn the primitive. It's like if you wanted to build a house. You can't really build the house before you learn how to use a hammer and how to hammer a nail into a piece of wood. And so a lot of times I know it, you feel like you kind of got to make it through a hump here early on where you can't quite do what you want to do, and what we're doing may feel a little bit boring at times. But again, we're learning how to use a hammer right now, so to speak, right? And even though it may not seem like we're doing much, you're learning all these fundamentals that once you really get them mastered, I guarantee you'll be able to walk out of these courses and really feel very well prepared to really build some neat things and to even learn some new languages, whether it's in mobile app platforms or web app platforms or whatever it is. So, without saying anything else on that front, we are going to take a look at Java primitives. Okay, so a few of the things we're going to cover in this lesson, we're going to cover a ton of fundamentals. I'm going to take my time going through this so you really understand these things well. First thing we're going to do that's going to be brand new is using the scanner. We're actually going to be able to read information from our user. In the last lesson, we basically wrote information to this little white box called the console. Now we're going to allow the user to actually type things in down here. We're going to read that, and we're going to process information from the user. So that'll be one really cool new thing we do. We're also going to learn a little bit more about the printf command, that print format. We're going to use that to format some numbers in some new ways that we had not done. And then the main objective here is to learn all about how we represent some of these basic data types, whole numbers, numbers with decimal point, and then some miscellaneous data types like booleans and characters. So before I go even into code, I want to give you a little bit of background that I think is really critical. And I don't want to go too deep into this, but I want to give you the essentials. Okay, so you've all probably heard binary, and if you haven't heard binary, you for sure heard zeros and ones. If you've ever seen the old, it's old now, but the Matrix, right? If you can kind of imagine that movie where whenever they see the computer screen with the green writing, it kind of has all these characters, right? We typically think of that as computer code, as a bunch of zeros and ones, right? And we kind of have this notion that computers operate on zeros and ones, 0, 0, 1, 1. But what does that really mean? We're not really going to answer that question necessarily in this topic or even in an intro type of course like this. You'd really want to go deeper into something like an architecture course to really get the answer to that question. But I want to at least kind of give us a basic understanding of what are zeros and ones. Okay, when we say computers operate on zeros and ones, what does that mean? Okay, well, zeros and ones are nothing really. It's just an abstraction. Okay, so what do I mean by that? It doesn't really mean anything in the physical world. Okay, it's like a language. If I use the word table in English and I said, hey, everyone look at the table, you guys would all know what to look at. You're probably sitting at a table, your laptop's sitting on a table, right? So you would look down and see the table right in front of you. Likewise, if I was speaking another language, maybe in Spanish or something like that, I might say something like la mesa. Okay, and so maybe you would have an understanding that, oh, that word means table. Okay, so whether I'm using the word table or the word mesa, right, those are both just abstractions for some physical world object, some real world physical object that I could go and put my hands on. Okay, because zeros and ones are kind of like that. Zeros and ones don't really mean anything, but they point us to something else, just like those words table and mesa point us to a piece of wood or something like that. So at the core, computers are made up of electrical signals. So we all know that we plug our computers into the wall, they get electricity, right? And they kind of operate on electricity, or maybe I have a battery that's storing some electricity and operating my computer. So at the very low fundamental level inside of your computer, inside of your processors, there are basically just two signals. There's high voltage and there's low voltage. Okay, everything that's done in computing, literally everything that's done in computing, is a high voltage or a low voltage. Okay, everything that's stored on your computer, you can think of it as a high voltage and a low voltage. That's not exactly true, but it's mostly true. Okay, and we represent a high voltage as a 1 and a low voltage as a 0. Okay, so why I said this wasn't exactly true is because we can store these high and low voltages in different formats, like on a hard drive, an old spinning drive. You might store the zeros and ones as magnetic spins or something like that. But we can store the zeros and ones on memory sticks, on hard drives, SSD drives, all kinds of things. Okay, now what can we do with a bunch of zeros and ones? Well, pretty much everything, you know. And here's a kind of the picture of the matrix I was referring to earlier. Well, movies, right? They're just a bunch of zeros and ones. Music, the waveforms, just a bunch of zeros and ones. Photos, each pixel in a photo, bunch of zeros and ones. Games, right? The physics behind it, the trajectory of the Angry Bird here, zeros and ones in the underlying surfaces. It's all it is. It's encoded into zeros and ones. And then maybe not quite as complex as movies, music, photos, and games are texts and numbers. Okay, we know we can get out our text messages, a super old iPhone, but we can get out our iPhones and our Androids, and we can type letters in there, right? And numbers, we can do calculators and stuff like that. So you may be wondering, but how, right? How do I represent this incredibly complex, these incredibly complex ideas and data as just a bunch of zeros and ones? Okay, well, the answer is binary encoding. Okay, representing data as zeros and ones. Now we're going to leave the movies, games, music, and all that really cool stuff for another class, right? That's pretty complicated, although I could explain it in a few minutes, but it's just kind of beyond the scope of what we're really trying to do here. What we're going to look at is we're going to look at some simple examples of really letters and numbers. And really we're just going to take a look at numbers in particular and how numbers are encoded in binary, and then maybe in a future lesson we'll eventually get around to looking at text. Okay, so I have a question for you. Did you take math in elementary? Okay, maybe you're in elementary school right now, and that's great. You are ahead of the times if you're working on learning some Java code right now. So did you take math in elementary? And the answer is probably yes, right? So what you learned in elementary is that a number, right, a decimal number, when I say decimal I mean a base 10 number, can be represented as the sum of the powers of 10, okay? And 10 is the base of the number system that we use because there's 10 characters in the alphabet, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have the sum of the powers of 10 with coefficients in the base 10 alphabet 0 through 9. Okay, so that may not make any sense, that sentence right there, but I think this will make perfect sense to you down here, right? If I have a number 2,485, well, my question to you would be, is 2,485 equal to this expression right here, 2,000 plus 400 plus 80 plus 5? And hopefully the answer to that question in your mind is obviously yes. Okay. Well, if that's true, then you could probably start to break this down, right? Well, can I break 2,000 into 2 times 1,000, 400 into 4 times 100, and so on and so forth? Okay, and then if I just break this down just a little bit more, you can see the pattern here, the 1,110 and 1. These are all just powers of 10. Okay, so we can likely or also say that 2,485 is equal to 2 times 10 to the third plus 4 times 10 squared plus 8 times 10 to the 1 plus 5 times 10 to the 0. And of course, anything raised to the power of 0 is equal to 1. Okay, so hopefully that makes sense to you, right? You can see that, and it may be bringing you back all kinds of good or bad memories from elementary school, but hopefully that breakdown of math makes sense to you. Okay, well, the cool thing is binary works just the same. Okay, so we have a decimal number, and anytime I say, well, typically when you say decimal numbers and we're talking like kind of computer science notation, I'm talking something with the power of 10. Okay, so here I kind of have this broken down, right? 2,485. The example we just looked at, I just kind of color-coded some of the coefficients here. I can do the exact same thing with binary. Okay, so binary is just a bunch of zeros and ones. So if I just have a bunch of zeros and ones, let's say I have 1, 0, 1, 1. Well, I can break that down just the same. Now, this may not make sense going from top to bottom. Let's go from bottom to top this time, right? So 1, 0, 1, 1. All I'm doing right here is I'm doing the same thing, right? I'm taking these coefficients, 1, 0, 1, 1, and I'm putting them right here, right? 1, 0, 1, 1. You can see the red, the blue, the brown, and the green, just like you saw up here, the red, the blue, the brown, and the green. And then instead of multiplying them all by the powers of 10, 10 cubed, 10 squared, 10 to the 1, 10 to the 0, I'm multiplying them by powers of 2. 2 cubed, 2 squared, 2 to the 1, 2, 0. And what you'll see if I go back up, right, 2 cubed is 8, 2 squared is 4, 2 to the 1 is 2, and 2 to the 0 is 1. Well, if I just multiply all these pieces together, right, 1 times 8 is 8, 0 times 4 is 0, 1 times 2 is 2, and then 1 times 1 is 1, okay? And you add those up, and that equals 11, okay? So remember, everything at a computer is just zeros and ones. So if I want to store the number that we understand to be 11, then the computer would store that with 1, 0, 1, 1. Or in the actual computer, the underlying kind of physical hardware, it would store a high voltage, a low voltage, a high voltage, and another high voltage. Okay, so that's the short version of how our base 10 number system is basically converted to a bunch of zeros and ones, a base 2 or binary number system. Okay, so let's give this a little bit of a practice here. Okay, so let's say I have a number like this, 1, 1, 0, 1, 0, 1. Okay, so you can see I have 1, 2, 3, 4, 5, 6 different digits, binary digits. Okay, and each of these digits has a power of 2 represented to it, right? Just like here, we had, right, this was the power of 0, the power of 1, power of 2, power of 3. We'll do the same thing here, right? We'll start on the right-hand side. We'll say power of 0, power of 1, 2, 3, 4, and 5, and basically however many digits that we have, okay? And then I'll go ahead and I'll basically multiply the actual value in the binary number times the power, right? 2 to the 5. 1 times 2 to the 5, right? 1 times 2 to the 4. 0 times 2 to the 3. 1 times 2 to the 2, and so on and so forth, okay? And then I just multiply these, so obviously wherever there's a 0, that's just going to get canceled out. And I just add those pieces together, right? So that essentially gives us 1 times 32 plus 1 times 16 plus 0 plus 4 plus 2 plus 1, and that equals 53. Okay, so that's just a second example of how I would convert binary to an actual base 10 number, going back and forth from that way. Okay, so to kind of lead us into what we're ultimately going towards is a concept of primitives. Okay, we have a bunch of data types, and in order to understand all these different data types, we have to understand a little bit of binary first. Okay, so the last question that we're going to talk about is, given a bunch of zeros and ones, how many distinct combinations can I represent? How many distinct values could I encode with a bunch of zeros and ones? Okay, so let's say that I had 2 digits. Okay, and each digit can be a 0 or a 1. Well, how many unique combinations of zeros and ones can I come up with? Okay, and the answer would be 4. Okay, so that's basically going to come out to 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so you can see I have 4 combinations, combos 1 through 4. In the parentheses here is the actual base 10 value that's represented by this binary. So this 0, 0 corresponds to 0 in decimal in our base 10 number system. 1, 0 corresponds to 1. I'm sorry, 0, 1 corresponds to the base 10 number 1, and so on and so forth. Okay, so with 2 binary digits, I could represent the numbers 0, 1, 2, and 3. Okay, so you'll see I basically have 2 to the 2 equals 4 unique values. Okay, so let's do one more. Let's say that I have now 3 binary digits. Okay, how many distinct unique values could I represent with 3 binary digits? And the answer is 8. Okay, so you can see 8 combinations. I can basically represent the numbers that we typically think of. Again, our base 10 number system, I could represent the numbers 0 through 7. Okay, so you can see 2 to the 3 equals 8 unique values. Okay, so hopefully you can kind of see the color code here. The red is the fact that we're using a base 2 number system. So that's the red, the base 2 down here. And then the blue, right, this number right here comes from the number of digits that we are using. Okay, so in general, in general, we can represent 2 to the n unique values with binary, where n is the number of binary digits that we have. Okay, so with 2 digits, it's 2 to the 2. With 3 digits, it's 2 to the 3. Okay, so that's just one thing to remember. 2 to the n, where n is the number of binary digits, that's how many unique values I could represent. Okay, so hold on to that thought. We'll come back to this slide if we need to as a reminder. But what we're going to do now is we're basically going to jump into some code, and we're going to start now talking about some of our primitive data types, because essentially what we're going to see is these primitive data types, really a lot of them do more or less the same thing, but they just have a different number of digits, binary digits that are storing the data in those particular variables and primitive data types. Okay, so we're going to do a bunch of stuff here, but let's start and focus on whole numbers. Okay, so we can store whole numbers in our code. Okay, now we did this in lesson 1. If you kind of look back to lesson 1, we started off with integers. If you recall from that lesson, we basically saved the value 5 into this variable called num workdays. Okay, so if I didn't do this, but if I had done something like 5.5, that would actually give me a compiler error. If I hover over, it basically says, hey, I cannot convert a double to an int. Okay, now we're going to learn all about why this is an error in today's lesson, lesson number 2. But this integer can only store whole numbers. Okay, so there's basically 4 different data types that we can store whole numbers with. And those data types are byte, short, int, and long. Okay, so int is short for integer. Now int is typically the one that we use, and I'll explain that a little bit later, why we use int typically. So I almost always use int, and sometimes I use long. And again, I'll explain why I do that a little bit later, but I want to motivate that with how these different whole numbers differentiate from one another. Okay, so let's go ahead down here. And in this code that we're going to write today, as far as some kind of purpose for this program, it's not going to achieve anything too much other than just really teaching us about primitive data types. It's not like we're going to create a calculator or anything like that. It's really just the code is almost going to be self-commenting. When it prints out, the printout statements that print out to the console are really going to teach us directly about Java and about programming languages themselves, rather than really help us build something interesting. Okay, so anyway, without saying anything else, let's take a look at the byte data structure. Okay, so I'm just going to kind of write a little bit of printing statements. So System.out.println. And I'm just going to kind of preference this, the byte data type. Okay. Now these primitive data types, there's basically 8 primitive data types, and we're going to go through those over the course of this lesson. The primitive data types are just data types that are built into Java. I don't have to do anything special to have access to them. They're so basic and so useful that Java just bakes these right in by default. So again, I'm just going to go ahead and print out a little bit of formatting here. I'm just going to kind of draw a bunch of lines right here. It doesn't matter how many, you can just put a bunch of equal signs there. Okay, so I'll go ahead and just play this program, make sure it works. Okay, so it's printing out the byte data type. Okay. So what I want to do now is I want to kind of represent and talk about how these data types are encoded and how many binary values these data types include. Okay, so I'm going to go ahead and I'm going to create an integer. All right, and I'm going to basically say int num bits is equal to 8. Okay, so essentially, the byte data type uses 8 distinct binary values to represent numbers. Okay, so just like we talked about here, in this example, we were using 3 binary values to represent 8 numbers. Likewise, the byte data type is going to use 8 distinct binary values. Okay, so whenever we use the word bit, that basically just means either a 0 or a 1. Okay, so I'll say a bit is either a 0 or a 1. Okay, so again, 8 bits are used to store the byte data type. Okay, now there's another very common term we need to discuss, and that is the byte itself. Okay, so you've probably heard bits and bytes most commonly in storage, right? You may have a 1 terabyte hard drive or a 500 gigabyte hard drive. You may have heard bits in the context of your internet bandwidth, right? Maybe you have a 100 megabit connection or a 500 megabit connection, or maybe someone says you have a gigabit connection. Okay, so you just need to pay attention to those few letters, those words, when someone says bit versus byte. Okay, so a byte is basically equal to 8 bits. Okay, so a byte is equal to 8 bits. So I could basically say num bits divided by 8. Okay, so I'm just going to say here 8 bits equals 1 byte. Okay, so this math should compute out properly, right? The number of bytes in this byte data structure is equal to the number of bits divided by 8. Now, obviously, the data type itself is called a byte, so it kind of lends its own name to the fact that, hey, there is 1 byte of data in this data type, and 1 byte is equal to 8 bits. So, with that said, I'm going to go ahead and write a little printout statement to kind of display this to the user. Okay, so we'll do a System.out.print line. Actually, do a printf. Okay, and I'm going to write a kind of a long sentence, and we're going to do this really the same thing for all of these, but we'll start to we'll really work hard on this first one or two, and then we'll do a lot of copying and pasting and kind of modifying for the different data types. So I'll say something like this: the byte data type uses, and I'm just going to start off, do %s bytes, byte or bytes. Make sure we get, Eclipse can sometimes think it knows what we're doing and it jumps around, so pay attention. It may have jumped your cursor around a little bit. Okay, and then I'll put in parentheses s bits. Okay, and I'm just going to stop right there, and we'll keep on going with this in a second, but for now I'm just going to print out this one little thing, and then I want to replace this %s. Remember, the first one is the number of bytes, so I'll put num bytes, and then I'll use num bits. Okay, so hopefully when I print this out now, it says the byte data type uses 1 byte, 8 bits. Okay, so that's great. So we've got kind of this concept of num bytes and num bits. Okay, now how many distinct values can I store in a byte of data? Okay, well, let's go ahead and get out a calculator to kind of help us out here. Okay, so if you recall from our binary PDF here, the last thing that we learned was we can represent 2 to the n unique values with binary. Okay, so where n is a number of binary digits. Okay, so let's go back to our code here, and in this case I have 8 bits, so I can represent 2. We might need to get a better calculator. Let's go to a scientific one. Here we go. Okay, so I can represent 2 to the 8, which equals 256. Okay, so with 8 bits of data, right, that means I've got 1, 2, 3, 4, 5, 6, 7, 8 different zeros and ones. I can represent those zeros and ones in 256 different combinations. Okay, so typically when we're storing numbers, we want to store both negative and positive numbers. Okay, so if you just kind of think about it, 256 values. In our binary PDF here, we were saying, well, 3 digits can store 8 values, so maybe I store the numbers 0 through 7, right? 8 distinct values. In reality, we typically want to make half of these numbers positive and half of them negative. So in this case, if I could store 8 distinct values, I would probably make 4 of them negative and 4 of them positive. So maybe I could represent numbers from about -4 to +4. Those are small caveat in there, and I'll explain that in just a second. So that's the general thinking here. Okay, so what we can actually do here is I'm going to go up and create a variable up here, and I'm going to create a byte data type. Okay, so this is the byte data type we're working with. You'll notice these primitive data types, they'll turn kind of like this purplish maroon color in Eclipse. So I can say byte, I'm just going to get the minimum byte number value. Okay, and I can actually get this using something called the byte wrapper class. Okay, this all what we're going to see in this particular program is that all of our primitive data types also have something called a wrapper class. And a wrapper class, all it is it's almost always the primitive data type spelled out, but with just a capital letter. Okay, the only exception is integer. We'll spell out integer completely, but we'll get there when we get there. Okay, but anyway, you'll notice that this byte wrapper class, I can just kind of write out the word byte and then a dot, and you'll see all kinds of stuff pops up. There's methods and variables and all kinds of things. So what I'm going to actually do is I'm going to get the minimum value. This will basically tell me the smallest possible value that I can represent with the byte data type. And I'm going to do the same thing for bmax. So byte.max value, and make sure you include the semicolon at the end there. Okay, so now what I can do, okay, is I can say the byte data type uses, 1 byte 8 bits, and I'll keep on going on with this, right? And I'll say something like this: to represent, and I'll go ahead and just kind of start this off easy, and I'll put %s, %s. Okay, and then I'm going to go ahead right here, and I will say I'll replace this first %s with bmin, and the second one with bmax. Okay, so there we see the byte data type uses 1 byte or 8 bits to represent numbers from -128 to +127. Okay, so if you remember from our calculator, we had 256 distinct values, and if I divide that in 2, right, that basically says 128 are going to go to the negatives, 128 are going to go to the positives. So why am I only seeing 128 on the negative side, but on the positive side, I'm only getting 127? Well, the reason is because I have the value 0, right? So if we kind of break this up just a little bit more, what I would do if I want to kind of clean this up to make it a little bit more proper, I would say to represent negative numbers from, and I'll put the S here, from that minimum number to -1, and non-negative numbers from 0 to that maximum number. Okay, and then I'll put a period, and I'll put a new line character right there. Okay, so let's go ahead and play this. So then you'll see the byte data type represents negative numbers from -128 to -1, and non-negative numbers from 0 to 127. So notice I'm not saying positive numbers, I'm saying non-negative, just because I have this 0, right? So that 0 is basically the 128th value. It's not quite positive, but it's not quite negative. So that's the byte data type. Okay, now the next thing I want to do is I want to actually read in a byte data type from the user. Okay, so I'm going to actually go ahead and move this prompt user from input, read input. That should be down here. So I'm going to Control X to cut that. Control D in Eclipse will delete an entire line at a time. So it's kind of a nice little shortcut. And I'm going to paste this down here. So prompt user for the input. Okay, so I'm going to go ahead and ask the user. I'll say System.out.println. Actually, no, I'm going to do a printf again. And I'm going to say, please enter a whole number within the range of %s, %s. Okay, and then I'll close that with the quote. And then I'm going to plug in my bmin and my bmax. Okay, so I'm basically asking the user to enter some value. So go ahead and run this. Please enter a whole number within the range -128 to 127. Okay, and then I'm going to go ahead and read this in. So I'll say byte b equals, and now we need to actually figure out a way to read in information from our user. Okay, so we're going to do something new that we've never done before. All right, so I'm going to actually comment this line out because I'm not quite ready to use it yet. What we need to do is we need to scroll up a little bit higher, and you'll notice there's a comment. A scanner allows us to read in variables data from user. Okay, so what we're going to do is we're going to use this class called a scanner. Okay, now, I don't even want to use the word class. We're a little bit, that's pretty far advanced in terms of terminology. I'm going to use I'm going to use a dumbed down word. I'm going to say this thing called the scanner. Okay, and I'm specifically using saying this thing called the scanner because I don't want you to get caught up in some of the notation that we're going to use here. Okay, this will start to make more and more sense as we go on. Just a little bit of boilerplate, a little bit of syntax that we have to use to read in from the user. But don't worry if you don't quite understand all of this yet. But how I do this is I write the word scanner as a capitalize, and I'll just give this scanner some kind of name. I'll call it scan. I could call this anything, scan 2, scan 3, whatever. Okay, then I say equals new scanner system.in. Okay, and you'll notice some red squigglies here once you save. And so what you're going to want to do is you're going to want to hover over, and you're going to want to import this this scanner java.util. Okay, now what it's going to do is it's going to basically add a line at the very top of my code that imports this functionality into my program. Okay, basically, by default, I don't have this ability to read in text from the user from this console down here, so I import this functionality into my program. Now, let's just say that I just undid that. Let's just say that when you were importing, you clicked on the wrong thing, okay, and you'll see it still has an error right here. Well, all you really need to do is just go up to the top and delete that wrong import and save it, and then just come back, hover over, and import again. Okay, so Java Eclipse is really great in that it offers us a lot of these quick fixes. So if you ever see a red squiggly, just hover right over it, and it almost always, I would say like 80–90% of the time, it basically gives you a quick fix that is actually exactly what you want it to do. So make sure you click on that java.util and save it. Okay. Now the only thing I really want to point out here, again, don't worry about why is this called scanner and why is there this new thing right here. Just kind of take this for what it's worth. A scanner, what is a scanner? Well, it's something that scans something, right? And what is it scanning? Well, it's scanning the system.in. Well, what is that? Well, I don't know, but I do know I've been using System.out, and whenever I use System.out, it writes down to this console thing down here, okay? So it kind of makes sense feasibly, right, that when I scan the System.in, it's going to scan something from down here in this console thing. And that's exactly what's going to happen. Okay, so I create a scanner, and this scanner is now basically it kind of has its eyes out on this whole console area for anything that the user would type in. Okay, so what I'm going to do now is I'm going to come back down here where I was just prompted the user to enter in some whole number within the range of -128 to +127, and I'm going to say byte b equals scan.nextByte. Okay, so essentially what this is going to do is it's actually going to pause my program. Notice I'll run this right now, and my program is actually paused, and notice I can actually type now. Okay, I can actually type, and the program is actually kind of waiting. You'll notice that there's actually a red stop button right here. Okay, that means my program is it's running. Okay, if I hit stop, you'll see everything stops and I can no longer type. Okay, if I comment out this line right here and I run the program, you'll see that immediately the red stop button goes away. This program is done executing. Okay, so just want to point that out. When I do the scan.nextByte, the program will literally halt and wait for me to type something in down there. Okay, so once I type it in and I hit enter, it's basically going to save that value in this variable b. Okay, so then the last thing I'm going to do is I'm just going to print this out to the user. Okay, so I'll do something like this. I'm going to now just print System.out.printf. Okay, and I'll print out like the minimum value and the value that I read in, and the maximum value. Okay, so hopefully the number that they read in is something like this. We'll say, do a quote, we'll do %s is less than or equal to %s is less than or equal to %s. Okay, and then I'll come over here and I'm just going to put in b min, b, and b max. Okay, so let's go ahead and play that. And now if I type in the number 45, for instance, you'll see that negative 128 is less than or equal to 45 is less than or equal to 127. Okay. All right, now I'm just going to kind of add a little bit of formatting here. So I'm going to go ahead and do my escape character and add a T there. So that's going to kind of tab that over. So if I do my 14 again, you'll see it just kind of gives us a little bit of formatting there to work with. Okay, perfect. The last thing I really want to do here is let me actually try a value that is outside of this range, and I'll kind of show you what happens. Okay, let's say that I actually give it the value 128. Okay, so a byte cannot actually store the value 128. So what actually happens is I start to get something very bad. I get this atomic bomb going off in my program is what I always tell my students. This is called an exception. Okay, anytime you see this red text, it means something very bad happens. It means you did something that was unexpected. Okay, now it'll typically give you a specific exception type. An exception is just a fancy word for error. If you continue on with these tutorials later on, I believe it's like maybe the 4th module, quite a few lessons from now, we will cover exceptions in depth. Okay, but for now, don't worry about them too much other than trying to get a general understanding of what the error is telling you. And you see here, it actually gives us some pretty good information. It says value out of range, value 128, radix 10. This is really just getting at base 10. Okay, so if I give it another number, let's say some huge number, it's going to give me the same error. If I give it negative 129, same error, right? It's out of range. That's just to basically show you the range of these numbers is exactly like we're showing here, from negative 128 to positive 127. Okay. Now there's one more thing I want to do up here. Okay, I'm just going to kind of do a little bit of math right here. And I'm going to print out, if you recall from if I could get my slide back right here, 2 to the n unique values with binary. Okay, so we did this in a calculator, right? We brought up the calculator and actually computed 2 to the 8. Right? We said 2 to the 8 equals 256. We're just going to do that in Java really quickly, just to kind of show you one more new thing, how to compute powers, and to just really demonstrate. So this code is really, the output is really self-commenting and self-teaching how to use Java and really these basic data types which you're going to find in every single programming language, just about. So what I'm going to do is I'm going to do another System.out.print. We'll make this a printf, and so we'll just kind of do a little bit more commenting. We'll say thus a byte. This is the byte data structure. Looks like I have an extra space here. No, I don't. Okay, so thus a byte can represent %s distinct values. Okay, and what I'm really doing is I'm going to compute 2 to the %s equals %s. Okay, so we'll again. Clips kind of jumped around on me a little bit. Okay, so what I'm going to do here is I'm going to replace this first %s, right? Thus a byte can represent %s. I'm going to replace this with the power computation. So what we're really trying to say is math.pow. Okay, now this is something brand new. We've never used this math class before, but this is if you ever want to do something a little bit more complex than adding and subtracting, and we're going to get to basic math later. You'll see in lesson 5 we're gonna do all kinds of stuff with addition, subtraction, and math, min, and max. But for now, I'm just going to use this thing called the math class, and you'll see when I hit dot, there's all kinds of mathy things available. You can see cosine, and there's probably sine and absolute value and min and max and all kinds of stuff. We're just going to use the math.pow. Okay, and the way that this works is I just pass it two different values. I pass it a base value, which for us is 2, and I pass it an exponent, which for us is going to be num bits, right? So remember, from our little PDF here, right? 2 to the n, where n is the number of binary digits. So in our case, 2 to the num bits, which is going to be 2 to the 8, right? So that's this first value, that how many distinct values, and then over here we have %s. Okay, so 2 to the num bits. Okay, equals, and I'm just going to basically do the same thing right here. Okay. And actually, I'm going to do this a little bit different. On this first one, I'm going to compute this a little bit differently, right? So I'm going to actually use the minimum value and the maximum value, right? It's going from negative 128 to negative 1, okay? And then it's going from 0 to 127. So I can represent this a different way. I can basically say, well, B max, right, which is going to give me 127 values, right, plus one more, right? So that's going to get the 127 from 1 to 127 plus the 0, right? So that should be 128 values plus the math.absolute value of B min. Okay, so again, remember B min is negative 128. So what I'm doing is I'm adding 127 plus 1 plus 128, and that should equal 256, which should also be the same mathematical value as 2 to the 8. So let's go ahead and play this, and we see, thus a byte can represent 256 distinct values. 2 to the 8 equals 256. Okay, perfect. So, well, not quite perfect. You can see I have some formatting issues right here, so I'll go ahead and I'm going to add at the end of this statement a new line character. Okay, and then I'll play it one more time. Okay, so we got a little bit of got at least a new line right there. I'll go ahead and put a period here since I added one up here. Okay, now the other thing I'm going to do is I don't really particularly like the fact that there's a 0.0 on here, right? 2 to the, you know, some whole number to some other whole number, a power raise is always going to be a whole number, okay, for us. We're always going to do like 2 to the 8 or 2 to the 16 or something like that. So I want to teach you something new about this printf. You remember one of the things we were going to learn is a little bit more how to use the printf command. Okay, so what I want to do is I basically want to print out this 256, just the whole number value there. Okay, so the way I can do that is this %s is kind of like a generic key. So anything I can pass a byte, I can pass a integer, a string, all kinds of different data types. Some of them we've talked about, some of them we haven't. And %s will just kind of print it out generically. However, if I hover over printf, you'll notice it kind of brings up some little comments about how this printf works. You'll notice this little link on the format. It says format string syntax. So this is a really handy little guide right here. This actually just brings up a web page. If you scroll down a little bit, I would encourage you to really take some time and read through some of this. But if you scroll down a little bit, you'll basically see this s. Anytime you have that %s, it just says, hey, if this argument that I pass in implements formatable, it basically prints it out somehow. Okay. However, there are some other little particular key codes we can use in addition to just the s. Okay, so in addition to s, we can also do the ones that we're going to look at are d. Okay, if I want to format a number as a decimal integer, which we've been doing just fine, but we'll look into that a little bit later. Or what we're actually going to look at is f. Okay, the result is formatted as a decimal number. Okay, so if I actually look at this %s right here, right, it was the 1, to third %s, right? So I have to go and look at the very last argument in here, okay? We have 3 arguments. The first one, separate byte of the commas, was this chunk. The second one was num bits, and the third one was here, okay? This math.pow is actually, even though we pass it into integers, 2 whole numbers, it actually is returning a decimal number. Okay, and that's called double. We're going to get to that a little bit later. We're going to talk about decimal numbers actually in this very lesson. However, this is returning a decimal number. Okay, so it turns out I can also use the F to format that. Okay, now if you recall, the D was for decimal integers, right? Basically whole numbers. So if I try to do a decimal, if I try to do %D and format this decimal, like this decimal point number, I think this will actually give me an error. Yeah. All right. It basically says, hey, you're trying to convert this number that has decimal points to a whole number to print it out. So what I need to do is actually need to do it as a F. Okay. And this will allow me to print it out. And you'll see that actually made it worse, okay? Because it's now printing out a bunch of decimal points. We're now basically saying, oh yeah, this number is for sure a number with a decimal point when we format it using this, it's called a floating point formatter. The F stands for floating point. Again, we'll talk about that in just a little bit later in this lesson. So anyway, what I can do here, just a little bit of syntax, is I can actually put a dot. And this dot signifies that whatever number I put after this is how many decimal points to print out. So if I put 4.4, you'll see it now will print out exactly 4 decimal points. Okay, so if I do .2, it'll print out 2 decimal points. Okay, so this is a really popular, useful one if you're kind of working with currencies. If you want to say like $22.42, then you can do that .2f. Now in our case, I actually don't want any decimal points, so I'll just do .0f. Okay. Okay, so perfect. So now we see 2 to the 8 equals 256. Okay, so I think we've done just about everything I wanted to do for this first data type. Okay, so this is really the foundation, and we're really going to use this same code over and over again for the next 5 data types. To really explain some of the differences between bytes, shorts, ints, and longs. Okay, so just to kind of review this little subsection, what do we do? Okay, so we talked about the byte data type, and the byte data type is represented with 8 bits. 8 bits is equal to 1 byte, obviously, but hence the name byte. And with those 8 bits, we can represent 256 distinct values, right? Because 2 to the 8 is equal to 256. And those values range, we can represent negative numbers from -128 to -1, and non-negative numbers from 0 to 127. Okay, so if I give a value, if I try to store a value like 128, it's just not going to work. We're going to have a big fat error in our program. If I try to store a value like -129, not going to work. Big fat error. But if I want to store a value like 89, perfect, right? Because that is in the range of -128 to 127. Okay. All right, so we're actually going to pause right here, and in the next video we're going to pick back up, and we're going to basically take this little lesson that we did, and we're going to apply it to some of these other data types to see what the difference is between these data types, and we're going to learn a few more things about printf and wrapper classes and all kinds of really useful stuff in the next video. Okay, thanks. Hope to see you there.